Welcome to today's webinar. The topic today is residual stress meets facade, cold-formed glass in RFEM planning process. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the webinars, technical content of the website, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Ulrich Lex will be the presenter today. He works in the customer support team and he's the main responsible person for the development of the glass design add-on and also for the masonry design add-on and construction stages add-on. You can ask questions when you click at the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that should be for the moment all from my side. I hand over to Ulrich. Ulrich, it's your turn.
Thanks, Andreas, for your introduction. Also from my side, a warm welcome to today's webinar. The topic of today's webinar is a cold-formed glass, how it can be considered in RFEM, and how it can be designed with the add-on glass design. We want to take a look at this content in three parts. In the first part, we want to look at the modeling itself of the basic system. In the second part, we want to take a look at the modeling of this bending process, in addition with add-on construction stages. And in the last part, we want to take a look at the results. Why are we doing this cold-formed process? I can imagine two cases. In the first case, it's a planned state that we have a non-planar facade with a small radius, I would say, and it is easier to create the glasses in the plane area. And for the manufacturing of the installation process, will it be banded? The second case I could imagine is that there are done mistakes during the installation, and maybe the facade should be plain, but it isn't. So I have small differences to a plane state, and I have to consider these stresses additionally to my other loadings. So on this state, we can switch to RFEM and can start with some modeling. So at first, I want to take a look at the base data. For today's webinar, I have activated the add-ons construction stage analyze and the add-on glass design. As in standard is chosen the DIN 18008, and as a last part, I did some small changes when you work with small radius. Could it be necessary that you modify your tolerances a little bit? I did it from 0.5 millimeters to 0.1 millimeter. That is all what I changed. That's why I can continue with OK. Let us start with some modeling. For the basic structure, I want to create an plane surfaces with the dimensions of 0.9 meter for the width and 1.8 meters for the height. For this, I create a new thickness at first. And for the new thickness, I can choose my thickness type, glass composition. Here I can easily define my different layers. I want to use a float glass with the thickness of 4 millimeters. Today I want to use an air with thickness of 16 millimeters, and as a second part, a float glass with 4 millimeters. This should be today my composition for an insulating glass. But it would be possible that you create a different one. It's like you want. You also can create your own compositions. You can save your compositions here as a template, or you can read it in your templates directly with the composition you have created before. Here also only laminate glass or a triple insulated glass would be possible. Okay, when you created your composition, we can continue with OK. As a next step, we can create our surface. We use here as thickness our glass composition, continue with OK, and can create our surface 1.8 to 0.9 meters. So now we have created the surface. At the down part, I want to divide my lines by distance, maybe 100 millimeter start. I want not divide it directly. I want to use today the node on line, and the line is not divided. Okay, and a second time with this I have the possibility to assign here nodal supports, maybe for the self-weight. Okay, as a next step, I want to take a look at the supports. Here I can use maybe line supports, create here a new line support, and say, okay, it's in global Y direction supported. Here I can also use a spring constant. It's maybe for helpful for the glass, for the peak stresses in the glass. I use now a high spring constant and want to support my lines outside. And for the self-weight, I create nodal supports. One which is supported in X and Z direction, X and Z. Okay, and the other which is only supported in Z direction. So when we have done the settings, Then we can go to the glass design, and here to the glass composition model. This glass composition model is created automatically. It's now red marked because the lines are not so oriented how it is needed for the glass model. That's why I open with double click. Here I want to choose a solid model because of the insulating glass. It's only possible the solid model. I have here my layers, what I have assigned. I have here my reference plane where it is created. Here I can define my supports where they are located directly. Maybe here I can choose on layer 1 and 3, and in the middle 1 and 3 in the middle, 1 and 3 in the middle, and 1 and 3 in the middle. What does this mean? This means I have here my insulated glass, structure, and it is the supports are created on this place and this place. When I say it's only on layer 1, then only one side is supported, and the same is when I say it's on the top, then on this location it's created. The same I want to do for the nodal supports. Here I support each glass surface in the middle. For the insulating glass, I have only the setting for the spacer. Today I want to activate an user-defined spacer. Here I have to create a thickness for the side wall. I create a new thickness. I copy this glass composition, a new thickness, and use here maybe a small E-module with a small shear module. Okay, and the thickness maybe 5 millimeters. Okay, and can then continue with apply. Here I get my message that some lines are not in this direction oriented where I need it. That's why I can set the required rotation and continue with OK. Now it's not anymore red marked because my lines of the system are rotated. So what is happening in the background? Solid sets, I do not need to see it. What is happening in the background? We can switch on the glass composition model, and here we see that my insulating composition is created. I have on the one side my first glass thickness. It's created with 2 solids. I have my space, my air area, and on the second side my glass panel. The supports are created also in the middle as we defined it, and downside we have here our nodal supports. So here's okay. And now we are ready with our basic construction, what we have to define. At the next step, we can create the load cases. For today's example, I want to create 2 more load cases. So first one, I want to say maybe it's pre-stress, and the second one, I want to have a wind load. The self-weight I want not to consider today, so it's not needed. For the pre-stress, I want to assign here a load where I can create this bending process. But for this, more with the next steps. Okay. For the wind load, I can here create a new load, set as a surface load, maybe 0.7. I want to have it locally and want to use maybe this surface number 18. It's not. Here are created 2 surfaces. The one surface is the thing what is deactivated for calculation, and number 18 is a part of my solid. Okay. And okay, and this I want to define it with minus. Okay, now we can go forward to the next step. For the next step, I want to create some things for the bending. This bending or this banded deformation I could create in some different ways. The first way I could imagine is to define any load. That I define any parabolic load and to have here some line supports with a spring constant, and in this way I could deform it. The other way is I can use here imposed deformations for nodals or lines. The disadvantage for lines would be I can only define a value on the line, in the beginning of the line and in the end of the line. And in between it would be linear. So it's not so good for a curved bending. That's why I want to use today nodal supports, nodal deformations. These nodal deformations I could define directly at the glass panel, but this could be the reason for some peak stresses or so on. that's why I create now a helper construction only to bring up here my imposed nodal deformations. So this I want to do by copying the line. I create a copy, maybe in Y direction, 5 millimeters. Okay, and the same downside. Okay. This line, the deformation at the beginning should be 0, and the deformation at the end should be around 12 millimeters. That's why I can start maybe here with my nodal imposed nodal deformations, and I can divide by distance from the end 100. Okay, so it's only starting from here, and the same here. Divide line distance 100. Okay, and I do not need this part. So these lines, I want to assign edit line a member. Here a member with a cross section. It doesn't matter. I choose now a steel cross section with a dimension of 5 to 20 millimeters, but it doesn't matter. It's only to bring the load to the glass panel. So it doesn't matter which cross section here is used. Okay. And I want to define this member into seven parts. Okay, I choose here a dimension of a delta of 10 millimeters. And these points are now the points where I want to assign my imposed nodal deformations. So when I have created the member, I had to assign some supports. At the beginning of the member, I want to support it in Z, X, and Y direction. For the Y direction, a small spring constant. For Y direction, it's okay, and for Z direction, also a small spring constant. Okay. And here. And here. Okay. So at the end, I have to a small spring constant and fixed in y direction at the end. And in between, I only need an support in y direction, because otherwise it is not possible to assign an imposed nodal deformation. Okay. And here assign all these nodes. Yeah. Okay. 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 So as a next step, we have now created the member, the supports. Now I would need a connection from my member to the glass panel. This would be possible with an rigid link, maybe. There are 4 rigid links automatically created. This was done by the solid glass composition model. Here I can create a new one. It's from line to line. I choose here again my line 38. And as a second line, this one. I create here a new line hinge because it should not a really rigid link. So I create a new line hinge where I set a small spring constant in X direction. I need a connection in Y direction. And I set a small spring constant in Z direction. Okay. Okay. Here, when we look at the lines, we need a connection in Y direction, and in X and Z we set a small spring constant. The same I have to do downside. I choose here number 40 and here 51, and I assign this line hinge. Okay. Okay. So now we are ready with the modeling of the system. Here I created for the glass composition model. I said I deactivate the automatic spacer and create here an user-defined spacer. And when there is an automatic created spaces, then are line hinges created between this surface and the glass panel. it's up to the user if when there is the user defined one, but it is also possible to create it afterwards. So you can easily add here a line hinge too. When you use here types of lines, line hinge, and create here a new line hinge, we can say, okay, Vx is free. Then we can choose also these lines of the glass composition model and create here some line hinges. Please be careful, because when you change something at the glass composition model, then maybe this connection to these lines are lost. So you have to check it afterwards and maybe assign it a second time. Okay. And okay. So I want to show only that it is possible to modify also this glass composition model. Okay. Then we can continue with the loading. For the loading, we created already this load case 2. And now I want to define here some imposed nodal deformations. The shape of the bending do we have here now to create with this imposed nodal deformations. Here you have different options. I have now a list where I know in addition to my radius, the radius is here about 34 or 33 meters, and I have created a list which deformation each node does have. It could be also used here an formula, or created a formula, a user-defined formula to create your deformations. So I want to set it today manually, and used for the first one 0.148 millimeters, and assign it to these both nodes. Okay. Okay. Here I can show it. Here I can show it on the loads. Imposed nodal deformations. Here we can create the next one. Okay. So the next one is 0.5926 millimeters. Here's the second one. Okay. Apply. The next one is 1.59 here and here. Okay. Then we have 2.3703. Then we have 3.7036. Okay. The next 5.332. Then we have 7.259. $9.481. And as a last one, we have 11.9993. Okay, so now we created this imposed displacement. For this case, as I said, I defined only in x direction of the rigid links a small spring constant. When if you would you assign this displacement directly to the glass surface, then it would be needed to consider also the deformation in x direction, because otherwise you would get some internal forces what you not want, or high peak stresses in this point of acting loading. Therefore, this system is in my eyes a little bit better, where the x direction is nearly free. Okay. Now we have created our displacement, and at the next step we can continue with the stages, with the different stages, with this bending process. Therefore, I create here a new construction stage. At this construction stage, I have to define everything what is acting at the stage. And for our case, I would define 3 stages. At the first stage, I want to bend the system. At the second stage, I want to activate the line supports. This means the fixing at on the facade. And in the last stage, I want to deactivate my helper systems and this nodal displacements to design or to define then the wind load on stage 3. Okay, what we have to do? We have to activate the members. At the members, they are acting all members 1 and 2. So there are acting the surfaces, there are acting solids, there are acting some nodal supports and also one line support. There are acting the line hinges and there are acting rigid links. I check it on, I get here the tabs, and now I have to define which objects are acting. For the surfaces, I would say all surfaces acting. The same is for solids. For the nodal supports, here I have to choose. On the one side, my glass fixing supports should be acting, or the nodal supports on the glass pane, and I would say all other nodal supports should act too. Okay, as a line support, the line support should acting only this one on the left side, because here should be the deformation 0, and only on the right side should it be banded with this 12 millimeters. Okay. For the line hinges, there are all line hinges acting, and for rigid links, there are this both acting. This one and this one. Okay. Okay, when we have defined this, then we can take a look at this construction stage. When we activate it here, then we see exactly what is acting. I see that my supports are acting, and I see that my members and the glass surface are activated. So as a next step, I can define also the other 3 stages. I want to create a new stage. This new stage is following the first one. At the second stage, everything is acting as it was in stage 1. And for the line supports, there are activated the other line supports too. Okay. And for the last stage, I created a new one again. And here should be the members deactivated. Okay. And when the members are deactivated, then also the nodal supports which are connected to the members do not acting too. So the other things are the same as in stage 2. We can continue here with OK. And we can look at the system. So the first stage we checked already. So at the second stage, the fixing from the glass panel is activated, and as a last step, the helper construction is deactivated. So when we did this, when we already did this, then we can continue with the settings for the FE mesh. Here I can look at the mesh settings. For the glass, it is better to use an finer mesh. So I choose now 50 millimeters and can continue with OK. So as a next step, we can take a look at the loadings. I open my load case and combinations dialog. Here I have also the construction stage. On this place, we have to define which load is acting for which stage. And on stage 1, it should only acting the load case 2, my nodal deformations. As I said, I do not want to take a look at the sulfide, so I do not activate it today. Of course, for a completely design, you would have be activated too. On my second stage, it should again acting my load case 2. And in the stage 3, there should be acting the wind load, and my deformation load should be inactive. So for the construction stage, is it necessary or is it important to take a look at the static analyze settings? Because it's needed that the analyze settings for the load cases and or load combinations and the different stages has to be the same. So in this case, we have large deformation analyze, and the same is used for the load cases. So it is okay. Here maybe I can change our iterations and increase the number of load increments. It is sensible for insulating glass design. Okay. Exactly. And as a next step, I can look at the design situations. I do not want to take a look at the SLS, so I deactivate it. I only want to take a look at the ULS. Here I also can look at the combination wizard. I activate my static analyze setting, and here I can consider my initial state. That means I can consider my different stages. When I activate the check, I get a new tab, and here I can consider the different stages. Today I want to consider stage 1 and stage 3. When I do this, then the load combinations are created for stage 1 and stage 3. When I continue with OK and take a look at it, then I see I have created a combination with stage 1, where the stage 1 is considered, and automatically a combination is created where stage 3 is considered. The stage 3 is here considered with this item, and here's stresses and deformations from stage 2 are overtaken to stage 3. So when we have done the settings, then we can continue with the calculation, and we can try to compute the first stage. So we can easily choose stage 1 and try to compute it. So here the FE mesh is created, and after that imposed deformations are computed. We see here the 3 different load steps, and my deformation is here about 12 millimeters. So everything seems to be okay. And we can continue with the next one. Before I compute the next steps, we can look at the glass design. I forgot before, when you create your main surface, your basic surface, you can switch on and off your glass composition model. So you can look at this surface. Here you have the settings for the glass design. You have the design configurations according to the standard, and the deflections. It's okay in our case now. So we can here continue with OK. Now we can continue with calculate all, or with the glass design. With calculate all, we have to be careful, because then all load cases are computed too, and maybe the load case 2 or the load case 3 separate computed are not able, because of the missing different stages. So in the different stages, the different design supports are activated and not, and that's why it is better to compute the glass calculation. Then only the things are computed what are needed for the glass design. So here we see the calculation process of the internal forces, and after that the glass design is done, and then we can take a look at the results. Okay, now I get the results for the 2 different stages, for the stage 1 and for the stage 3. As usual, we have here all the results. On the one hand for the glass design, and on the other hand for the static analyze results. These are maybe the deformations or the stresses, in this case the solid stresses, and the sigma 1 stresses are necessary. And here you can compare it between the different stages and can do here the analyze. When we take a look at the glass design, we see that on stage 1 we have an ratio of 93% and for stage 2 48. This seems to be on the first view a little bit confusing because we would think that the stage 3 must have a bigger ratio, but this has an easy solution. It's connected to the design standard. For the design standard, there are for the load cases defined a load duration. The pre-stress or the imposed deformation is now considered as a permanent load situation, and our wind load is considered as a short-term load. And this is the reason why we have here, when we double-click, the factor 0.25 in the allowed stress for stage 1, and for the stage 2 we have here the factor 0.7 for the short time loading, and that's why we have a different design ratio. This is a fact on the standard. What would we need to take a closer look by the engineer, because I'm not sure how such imposed deformation has to be considered. It is not possible to mix both. Here in stage 3 are the imposed. Here is only for the ratio the factor 0.7 considered. It's not possible to mix the stresses from stage 1 with the factor 0.25 and the sum with a factor 0.7 for the stresses from stage 3. This is not possible, but this is solvable, I think, by the engineer. Okay, these results are, as usual, possible to document at the printout report, and this is the way how we can design and consider this cold formed systems with RFEM and the add-on construction stage analyze and the glass design add-on. That's all from my side. I would say thank you for listening and would give back to Andreas.
Thank you, Ulrich, for your presentation. At the end of the webinar, I have additional hints for you, for example, to our online courses. There's the RFEM 6 course, the course for beginners, then the Eurocode 2 course for the reinforced concrete design with RFEM 6, the Eurocode 3 course for the steel design, the Eurocode 5 course for the timber design, the Eurocode 8 course for the earthquake design, and the AI masterclass course for the use of artificial intelligence. For more information and prices, just scan the QR codes or click at the links here. You can get an RFEM 6 course or an Eurocode course for free when you submit your customer project and when we will publish it. Just scan the QR code or click at the link here to submit your project. A hint to our free online services. There's, for example, the Dlubal community. You can ask questions there, and our support team or other community members will answer you. Where's the GeoZone tool for the determination of wind, snow, and earthquake loads? You can download 3D models. Also, the trial versions of RFEM 6, RSTAP 9, R Wind 3, or R Section. Yeah, just try it. You can get more information on our website, dlubal.com. For example, can you find the knowledge base articles there, the recorded webinars. You can ask the AI assistant Mia all the time, 24/7. Yeah, just use it or just try it. Okay, that should be also all from my side. I thank you for your attention. Thanks again to Ulrich for your presentation. I hope we meet each other in the future webinar. See you then. Bye-bye.